All right, hello everyone. For this part 3 of our project, which I've confusingly labeled part 2 in our instructions because it's part 2 of the second part, so whatever. We're going to work on using our function equation now to extrapolate or interpolate. Now we talked about the meaning of that in class. You probably learned about it if you have ICP. Either way, that's what we're going to do here. So recall in the last set that we collected data from running an experiment by isolating a bunch of parameters and just changing one variable and seeing how it affects the other. We collected the data and we put it onto a spreadsheet and put it into Desmos. After making some quick modifications to Desmos, Desmos provided one of 4 equations that really fit the data very well. Now what we're going to do is to use that equation. So first of all, we'll observe that, let's go back here, that this was the equation format that I chose because it had the best fit for me, and the A value in the computer was negative 5.768, and this was the B value, and the C value, according to that, what's called regression, a curve of best fit. So this is the equation that I'm going to work with. Now recall, what we're trying to do is to use our newfound function equation so we can make predictions, essentially predict the future. I was curious as to what would happen if the drag coefficient was set at 14. Now, according to my graph, it looks like we will have a distance fired of about, looks like 14 or 15 meters away from the cannon. So I don't know if that's going to work or not. I don't know if it's true, but it looks like if I extrapolate my trend that that's what's probably going to happen. So here's what I'd like us to do so that we can get used to the notation and how to write mathematics. Select a value to either interpolate or extrapolate. In this case, I chose x equals 14. Then what we're going to do here is we're going to write out some mathematics in the old-fashioned way, if you will. So here's the equation that I had, and in my written work, I'm going to remind myself that the f of x in my equation, sorry, I should back up for a second. We use y in Desmos because it's convenient, but in handwritten work we use f of x. That's been discussed in class, but I just want everybody to make sure that they substitute their y with f of x so that we can follow the proper rules for notation that follow. Again, there's more discussion about this in class, but anyway, back over here, I'm going to define my variables very clearly in the corner so I know f of x represents the horizontal distance fired and x represents, in this case, the drag coefficient. So I've had my equation all written out. Now right underneath it I'm going to choose my extrapolation value, substitute that into the equation, so wherever there was an x I replace it with 14, don't forget the parentheses. Now you can see over here that I evaluated the first part of my equation with the calculator by typing in literally what I saw, and I got negative 20.777, so I transfer that here. Then I add the 35.809 and I get 15.03 meters. So I translate now, this mathematical equation has now a translation into English. This all means that if the drag coefficient was set at 14, the object should land about 15.03 meters away. So to finish up the experiment, I'm going to go back to my Cannon simulation and clear all this stuff out, set my drag coefficient at 14, and fire it up and see what happens. Well, it says I scored. Let's see what the actual distance was. It says 15.75. Now again, according to my calculations, it said about 15.03. I can and should verify those calculations in Desmos. Here, if I drag along the curve until x equals 14, my equation predicts 15.036, so that's what I got when I used my calculator. The equation predicts 15.036, and the actual simulation says 15.75. So I'm off by a little bit. In fact, what we can do now is play around with this. We can actually put in the point 14, 15.75, and what that's done is actually changed or morphed my equation. Now it doesn't fit so well. And it produces a number, though, that's closer to 15.75. So mathematical modeling is not perfect, and that's one thing that we want to learn from this particular unit. But sometimes we're going to pick a function that's an absolute perfect fit, and it will extrapolate correctly. But that's the nature of math and science. Sometimes we'll make a prediction, and the prediction will turn out to be off by some little bit. But that's not the point of this exercise, is whether our prediction succeeded or failed. The point of this exercise is to, again, learn about function language and how we talk about functions and how we work with functions, and put all those pieces together in a one neat project. So just looking at all these instructions, everything I showed you is all written down here for you to see, plus you can rewatch the video if you need to. And finally, I added a PDF file that shows some work from an experiment that somebody did last year. There's one thing missing from this, which you can read about, but in general, this is a great model. This is exactly what I want your work to look like. So do as much editing and picture pasting and doing whatever you need to do to get your work to look of a quality like this. Particularly if I'm going to be reading 50 of these, I'd like to see everything in the same general place so that I can look at people's work and know where to look and get on with life. So, all right, thanks for watching. Have a good day.